Hello! In this video, I'd like to look more closely at the connection between regular languages and paths through graphs. If we have a transition diagram for a deterministic or non-deterministic finite state automaton, then a word is accepted by that automaton if there's some path from a start state to a final state where the edges of that path are labeled by the successive characters of that word. I'd like to relate this to another tool for reasoning about paths through graphs if we're just interested in counting them. So given a graph, and this graph might have directed edges, that is, edges that only go in one direction from one vertex to another. So this edge here only goes from 2 to 0. It does not go from 0 to 2. But we can also have edges that go in both directions, which we'll indicate like this. So there's an edge from 1 to 2 and an edge from 2 to 1. The graph can also have loops, so vertices can be connected to themselves via a directed edge, and they can also have multi-edges. So here we have 2 edges going from vertex 0 to vertex 1, and we have 3 edges going from vertex 2 to itself. Of course, we don't have to have these features. We could be dealing with an ordinary graph, but you're perfectly allowed to have these features. Let's let p superscript n sub ij be the number of paths from vertex I to vertex j of length n. So for instance, if we're talking about paths of length 1, then we're talking about single edges, and we're trying to capture that information from the graph here. So for instance, p superscript 1, 1, 2, is the number of paths of length 1, the number of edges from vertex 1 to vertex 2. In this case, there's one edge, this one here, leading from vertex 1 to vertex 2. The number of paths of length 1 leading from vertex 0 to vertex 1 is 2. We have 2 edges leading from vertex 0 to vertex 1. The number of paths of length 1 leading from vertex 2 to itself is going to be 3. There are 3 different edges. And the number of paths from 0 to 2 of length 1 is 0. So these are just some examples of that information there. As a mathematician, it's always fun to consider what happens in the 0 case. So if we're interested in paths of length 0, so let's say we're trying to count the number of paths of length 0 from vertex 0 to vertex 0. So a path of length 0, there is a path of length 1 going from 0 to 0 along this edge here. But a path of length 0 doesn't go along any edges. Essentially, you're just staying put. But luckily, there is one way to stay put to go from vertex 0 to vertex 0. And that is you stay put. There is one sequence of 0 edges that starts at vertex 0 and ends at vertex 0. On the other hand, it's impossible to get from vertex 0 to vertex 1 without moving along any edges. So there are 0 paths of length 0 from vertex 0 to vertex 1, and so on and so forth. If we have p sub ij, this is going to either be equal to 1 if I is equal to j, right? There's one path of length 0 from vertex I to itself, and that's the you just stay put path, and there are 0 paths that will take us to a different vertex because we need to take some number of turns to get from one vertex to another. There's a very important recursive formula that these values satisfy. Suppose that we're interested in counting the number of paths of length n plus m from vertex I to vertex k. Right? So we're interested in a path from vertex I to vertex k, and we're interested in this path being of length n plus m. Now, let's say that after n moves along this path, we wind up at vertex j. And let's just count the number of paths that wind up at vertex j at this particular point. Well, there's lots of different ways of getting from vertex I to vertex j. In particular, there's p superscript n, ij of them, right? The number of paths of length n going from vertex I to vertex j. And then there's going to be lots of different ways of getting from vertex j to vertex k in m turns. Specifically, there's going to be p superscript m, jk of them. And so the total number of paths that go from vertex I to vertex k, stopping off at vertex j at this particular time, is going to be, we can pick any one of these paths here and any one of these paths here to be our path. And so we get to choose one path from a collection of this size and one path from a collection of this size. There's going to be the product of those two number of different paths from I to k that pass through j. But of course, not all paths from I to k are going to pass through this particular vertex j. They could pass through any of the vertices in the graph, including, so this diagram kind of falls apart a little bit if these vertices are the same, but the reasoning is the same. But the vertex j could be literally anything. And so what we want to do is we want to add up over all possible vertices that could appear after n turns along this path. So we're going to take the summation of this over all possible values of j. Does this formula look familiar? This formula here is the formula for taking the product of matrices. In particular, it's expressing the fact that the matrix P superscript n plus m is equal to the product of P superscript n and P superscript m. And that suggests that we shouldn't actually view this as a superscript at all, but rather as an exponent. And that this is just a really basic power law that p raised to the n plus mth power is p to the n times p to the m. And sure enough, if we create a matrix whose entries are given by the number of paths of length 1, that's going to give us p to the power first, that's going to give us a value of p. And in that case, the ijth entry of the matrix p raised to the power of n is going to give us this number here. So what does this matrix look like for this particular graph? Well, we already have some of its entries. Let's fill in the rest. So for instance, entry 1, 2, in the row indexed by 1, which is actually the second row, and in the column indexed by 2, which is actually the third column, we have a 1, indicating that there is one path from vertex 1 to vertex 2 of length 1, which is exactly what we said before and exactly what we see in this graph here. This matrix here is called the adjacency or transition matrix of our particular graph / finite automaton. And again, just by looking at powers of this matrix, we can very easily calculate the number of paths of any particular length from any particular vertex to any other vertex. For instance, if we consider p to the 0th, any matrix raised to the 0th is going to give us the identity matrix, and that agrees with what we have over here. In general, if we're looking at the ijth entry of this matrix, it's going to be a 1 if I is equal to j, and a 0 if I is not equal to j. But more interestingly, we can take, for instance, p to the power of 2 and count the number of paths of length 2 in this particular graph here. So for instance, we know that there are 5 paths of length 2 from vertex 2 to vertex 1. And it would be really kind of tedious to try to count those and make sure you had gotten all of them. But what are those paths? We have the path from 2 to itself, and there's actually 3 different ways of doing that. And then we go from 2 to 1, so that would be a path of length 2, and there's actually going to be 3 different paths because we can take each of these different edges. So there's 3 of those. And then we also have a path from 2 to 0 to 1. And we actually have 2 of those paths because we can take either this edge or this edge when we go from 0 to 1. So there's 2 different paths that way. 3 plus 2 is 5. And so we can get this count just by doing some basic matrix arithmetic without having to worry about accidentally counting the same path twice or missing out on one of the paths. These transition matrices actually work really nicely in the case that our graphs have labeled edges. So this here is pretty much a non-deterministic finite state automaton. We just need to specify some start states and some final states in order to turn this into the transition diagram for an NFA. And what we're going to do to construct this matrix, which we call an event transition matrix, is to simply let each of the entries in the matrix be the sum of the labels of edges from I to j. So the 0th entry is going to be the sum of the labels of the edges from vertex 0 to vertex 0. So there's only one, so that's A. Entry 01 is going to be the sum of the edges from 0 to 1. There's two of them. There's A and there's C. So this entry here is A plus C. The 02th entry of our matrix is the sum of all edges from 0 to 2. There aren't any, so that's just going to be 0. There aren't any edges from 1 to 0. There aren't any edges from 1 to 1. There's one edge from 1 to 2, which is labeled with a B. There's one edge from 2 to 0, labeled with a B. There's one edge from 2 to 1, labeled with an A. And there are three edges from 2 to 2. I've put the labels out here, but each of these edges has one of these labels. There's actually two edges from 2 to 2 that are labeled A. That's perfectly fine. We just represent that as A plus A, which we can write as 2A. And then we also have to add in a C. And so the entries of this matrix here are going to be sums, possibly empty if we have a sum of 0, of some natural number coefficient times one of these variables. Let's take this matrix and square it. Hopefully, p squared sub ij will tell us something about the paths of length 2 from vertex I to vertex j. So the entry here is going to be A times A plus C times 0 plus 0 times B. And the zeros go away, so we just wind up getting A times A. And sure enough, there's one path of length 2 from vertex 0 to vertex 0, and that's to go along this edge twice, to read in an A and read in another A. So in order to work out this entry of the matrix, we take A times A plus C plus A plus C times 0 plus 0 times A. Again, the zeros are going to go away, and we'll just be left with A times A plus C. Now, I'm going to want these variables to work pretty much just like algebraic variables, except I'm going to want the order of multiplication to matter. So in particular, I'm going to want to distribute this out to get AA plus AC, but I want this AC to be different from CA. And that's because I want this to reflect the paths of length 2 from vertex 0 to vertex 1. Well, the only way to get from vertex 0 to vertex 1 in two turns is to first take this edge and then take one of these two edges. So we have the path AA, and we also have the path AC. And I want this to reflect that exactly. I want this to say we can either take the path AA or we can take the path AC. And in particular, I'd like to distinguish this AC from a path labeled CA because there is no path labeled CA from vertex 0 to vertex 1. This entry here is going to be A times 0 plus A plus C times B plus 0 times 2A plus C. In other words, just A plus C times B. And again, I'm going to want distributivity, this time on the other side, to turn this into AB plus CB, because those are the paths of length 2 from vertex 0 to vertex 2. Right, we can take either the edge labeled with A and then B, or we can take the edge labeled with C and then B. This entry of the matrix here, I'd like to be 0 times 0 plus 0 times B plus B times 2A plus C. And I am going to want these variables to commute with ordinary numbers. So b times 2 times a should just be equal to 2 times b times a. As long as the variables stay in the right order, we can move numbers out to the front of products. And so this is going to distribute out to 2 times b times a plus b times c. And that's going to indicate that there are 3 paths from vertex 1 to vertex 2. 2 of them are going to be labeled BA, and 1 of them is going to be labeled BC. And in particular, that's just B followed by one of the 2 edges that's labeled A from 2 to 2, or BC following the edge labeled C from 2 to 2. This entry here I would like to be B times A plus A times 0 plus 2A plus C times B. And here's a situation where we'd like to treat these variables as not commuting with each other. I would like to not combine these as like terms to get something like a 3AB. I want to indicate that there's one path that reads BA going from vertex 2 to vertex 0, and there's 2 paths that read AB going from vertex 2 to vertex 0. We work out this entry. It's the paths from vertex 2 to vertex 1. It's going to be BA plus BC plus 2AA plus CA. And this entry here is going to be AB plus 4AA plus 2AC plus 2CA plus CC. So this is very nice. As long as we allow our matrices to include variables that don't commute with each other, we can get not only the paths, not only the sequence of characters that we have to read going along a particular path from one vertex to another, but we can actually get the multiplicity corresponding to that word, right? So this 4 here indicates that there's actually 4 different paths to get from vertex 2 to vertex 2 by a path of length 2 that read in the character A followed by the character A. So just like before, it's useful to consider the 0 case. What happens if we're interested in p to the 0th? Well, any matrix raised to the power of 0 is going to give us the identity matrix. But what does that mean? Well, these zeros are pretty straightforward, right? This 0 here indicates that there are no paths of length 0 from vertex 0 to vertex 1. So it's a sum of nothing. But what about this 1 here? There's one path of length 0 from vertex 0 to vertex 0. But we don't just want the path, we want the word corresponding to the path. But what is that word? What is the word that corresponds to the path of length 0 from vertex 0 to vertex 0? It's the empty word, right? We're going along 0 characters worth of edges. We're going along edges labeled by characters in the empty word. And so we want to view this 1 here as actually 1 times the empty word. So every time we see a 1 showing up, you should be thinking about it as a 1 times the empty word. A 1 times any character A to the 0th. Another way to look at this is just like how this term here represents that there are 2 copies of the word A that we're interested in for this term here. This indicates that there's 1 copy of the word, and then it's just all of the characters that we see after this here as a word. And well, that's the empty word. There are no characters here. So it's going to be 1 times the empty word. But of course, if we're reasoning about regular languages, we're not interested in paths of length 1 or paths of length 2 or paths of length 3. We're interested in any path going from a start state to a final state. We're actually interested in another matrix, let's call it p hat for the moment, but it actually has another name, whose ijth entry is going to tell us something about the number of paths of length 0 from I to j, plus, we found it very useful to consider plus as kind of like an OR operation, right? We can either take an edge labeled A or an edge labeled C. And we saw in the power 2 matrix that it kind of indicated a bunch of different choices of paths from one vertex to another. So we'll use plus again to indicate that we could either be interested in paths of length 0 from I to j, or paths of length 1 from I to j, or paths of length 2 from I to j, or and so on and so forth. We'd like to take this summation here. So we'd like to find a matrix that is this particular sum of matrices here, this particular infinite sum. And it turns out there's a very clever name for this particular matrix, and that's P star. Going along with, if we have a particular set of words A, then A star is going to be the empty word plus the words in A, which we could write as A to the first, plus words in A concatenated with itself, that is pairs of words, one word from A and one word from A, plus, or, right, we're thinking of plus now as the union of regular languages, or A cubed, words of the form some word from A followed by some word from A followed by some word from A, and so on and so forth. And to complete this correspondence, we should just view a particular language raised to the power of 0 as just the empty word, right? A concatenation of 0 words from the language A. So we're going to have to take a bit of a leap for a moment in terms of what sorts of entries we're going to have in our matrices. Before, the entries in our matrices were always polynomials with non-commuting variables whose coefficients were natural numbers. I'm going to want to extend that. I'm going to want the coefficients to be integers. We'll see why in a moment. And we're actually going to want, instead of having these entries be polynomials, I'd like them to be infinite polynomials. I'd like them to be non-commutative formal power series. So a power series is something like a basic Maclaurin series or Taylor series, but in this case we're allowing multiple variables, and so we can have some infinite sum of some coefficient times some sort of product of variables. And when I describe them as formal power series, that just means that we're not particularly concerned about convergence or divergence. If we were looking at these things from the perspective of real analysis, we'd be very concerned about whether or not these particular infinite sums converged or diverged with some particular notion of limit. Right? Instead of looking at an actual infinite sum, we're looking at the limit of the finite partial sums. And so we're really concerned about limits, and so we need to have some sort of notion of distance to allow us to define a notion of limit on this particular space in order to be able to make sense of infinite sums. There is a notion of limit on this particular space that allows these particular sums to converge, but let's not worry about that. Let's just consider formal power series where we don't worry about whether our series converge or not. And fortunately, when we're calculating this sum here, we don't actually have to worry that much. If we're considering a particular entry of the matrix P star, let's say the ijth entry, the ijth entry of P to the 0 is either going to be 0 or 1. And then this term of the sum here is going to be some sort of finite sum of a coefficient times a single variable, right? Some sort of finite sum of degree 1 terms. And this entry of this matrix here is going to be some sort of finite sum of degree 2 terms. And the next entry from P to the third is going to be some finite sum of terms of degree 3. And so what's actually going to happen is in this infinite sum here, we aren't going to have any like terms between these different terms of the sum. And so we don't actually have to worry about, say, having infinitely many a's, right? It would be really bad if we had an a term from this term of the infinite sum and an a term from this term of the infinite sum and an a term from this term of the infinite sum and so on and so forth. And so, morally speaking, we should have an infinity times a as a particular term showing up in our resulting matrix. That's never going to happen because the degrees of the entries that we're adding together always get larger and larger and larger. So again, we're just going to work out these infinite sums. We're not going to concern ourselves with questions of convergence, and we'll just kind of magically get the right answer. And of course, you can make everything formal using the theory of noncommutative formal power series, and I'll link to some resources where you can read about noncommutative formal power series in the description below. But I'd like to make one more connection. Let's say that we were considering this sort of sum, but just for an ordinary real variable, x. We actually have a nice formula for this infinite sum here, assuming it converges, which is 1 over 1 minus x. And we can actually do something like this for a matrix. We can take the identity matrix and subtract off our matrix P, and then instead of taking 1 over that, right, we still want to take the multiplicative inverse. We'll just take the matrix multiplicative inverse. Take the inverse of the resulting matrix. So in particular, this P star is actually going to be equal to the identity matrix minus P inverted. And just like how you can derive this formula here in the real variable case, you can also derive this formula here for the matrix case using exactly the same reasoning. So we find ourselves needing to invert a particular matrix. But here's the thing, I don't trust any formula that I could look up for calculating the inverse of this matrix. Matrix inversion formulas tend to assume that the entries of a matrix are going to be expressions representing real numbers or maybe complex numbers. In either case, they're going to assume that multiplication of the entries is commutative. And so we're faced with a particular challenge in adapting any matrix inversion formula that we might have, in that we have to figure out what order all of the products should be in that formula. Because suddenly the order that we multiply these things in matters. So what can we fall back on when trying to calculate the inverse of a matrix? Well, we can always calculate the inverse of a matrix using row reduction. But I actually want to investigate even further that process. When I first tried inverting some of these matrices using row reduction, I assumed that the natural generalization of the row reduction operation that multiplied all of the elements of a particular row of a matrix by a particular term was to be able to multiply all of the elements of a row by a particular term on either the left or the right, as long as we multiplied all of the terms on the left or all of the terms on the right. And when I did that row reduction, I got complete garbage. We need to look even closer into the process of using row reduction in order to invert a matrix. The idea is that we're trying to solve this equation here. We're trying to figure out what matrix can we multiply M by in order to get the identity matrix. And this multiplication here can be either on the left or on the right. We know that the particular matrix that we're trying to invert has both a left inverse and a right inverse, and that they're equal to each other, and that means that the inverses are unique. We don't have to worry about getting a different matrix if we try to invert on the other side, and we don't have to worry about accidentally getting a different inverse than the one that we actually wanted, P star. So in order to solve this equation here, we're going to want to apply row reduction operations to both sides of the equation. In particular, we're going to want to multiply both sides of the equation on the left by row reduction operation matrices. We're applying our row reduction operations to both M and the identity matrix, and in particular we're multiplying on the left. And because when you multiply two matrices together in the non-commutative case, the order that the variables show up in is the variables from R1 show up first, and then the variables from M. The variables from the left multiplicand show up on the left, and the variables from the right multiplicand show up on the right. We really can only multiply our rows by particular terms on the left. In order to multiply on the right, we'd need to maybe somehow slip in something multiplying on the right here, but we actually can't do that. The idea is that we're doing the same thing to both sides of the equation, and sure, we can on this side of the equation multiply by something on the right, but On this side of the equation, if we multiply by something on the right, it's going to wind up on this side of the unknown matrix. And that doesn't really correspond to what we were trying to do, which was to multiply m on the right by something. We really want to somehow slip a matrix in here. But we can't do that. We can only multiply our rows by terms on the left. So we keep going, we keep applying our row reduction operations until eventually our row reduction operations applied to m give us the identity matrix. And so this term here is going to be the identity matrix. Hopefully we can get down to the identity matrix, but if we can, this side of the equation is going to be the identity matrix times our unknown matrix, in other words, just our unknown matrix. And so our unknown matrix is going to be equal to this row reduction, this sequence of row reduction operations applied to the identity matrix, which incidentally is just going to be the single matrix corresponding to that series of row reductions. But that's not the interesting thing. The thing that we care about is that this right-hand side of the equation is our row reduction operations applied to the identity matrix. I'd like to work through a simpler example just so that the algebra is less messy. Here we have a much simplified graph and its event transition matrix. Our first step is to calculate the matrix I minus p, which winds up looking like this, and then we want to invert it by setting it next to the identity matrix and simultaneously row reducing the two matrices. Our first target in row reduction is to get rid of this negative a here. We're going to want to multiply the first row by something in order to turn this first element here into an a, and then add that to row 3 in order to get rid of this negative a. So the thing that we'd like to multiply row 1 by is a over 1 minus c. In general, in this algebra, we need to be a little bit careful with division, but we actually know a multiplicative inverse to 1 minus c, and that's c star. For any term in our algebra, x star is going to be the inverse on the left or the right of 1 minus x, and that applies in this case as well. So by multiplying row 1 on the left by c star, we can turn this first entry here into a 1. And then by multiplying on the left by a afterwards, we can turn this first entry into an a so that it will cancel out with the third row. When we multiply ac star by a, we can pull that minus 1 out front because we can always commute with the coefficients out front, but we need to be really careful about the order of the variables. We're multiplying row 1 by ac star on the left, and so we need to take the variables and multiply them on the left by ac star. And then multiplying the zeros and the 1 on the left by ac star is fairly straightforward. So this is our multiple of row 1, and we'd like to add this to row 3 to get our new row 3. So this is our new row 3 attained by adding a multiple of row 1 to the original row 3. Let me copy this up here. Our next target in row reduction is going to be this entry here. And to get rid of it, we're going to want to take a multiple of row 2 and add it to row 3. Specifically, we'd like to multiply this 1 so that it turns into a c plus ac star a. That is, we want to multiply 2 by c plus ac star a. Again, we need to be a little bit careful when multiplying our negative b on the left by this term here. And there's some distributivity going on here where the b distributes to both the terms in the sum. And I guess the minus sign also distributes. Let's now add this to our original row 3 in order to get our new row 3. And now I'll take our new row 3 and copy it up here. Our next target of row reduction is this element here. We'd like to turn it into a 1, and we can do that by multiplying row 3 by the appropriate term, by the multiplicative inverse of this term here. Well, this is 1 minus x for a fairly complicated x, but we know how to invert 1 minus x in this particular algebra. We can turn this element into a 1 by multiplying on the left by CB plus AC star AB star. So let's do that. And I'll just erase our original row 3 so that we have the next step of our row reduction. So I actually want to stop the row reduction here, both because it's gotten algebraically very tedious and because we've actually finished row reducing row 3. If we were to continue the row reduction process, we would be modifying rows 1 and 2, and we actually wouldn't be making any changes at all to row 3 of this matrix. It already looks like what we want row 3 to look like on the left-hand side, the third row of the identity matrix. So this here is row 3 of our inverted matrix. And we can check that this is indeed what we were looking for. We now have regular expressions that describe the set of all paths from vertex 2 to any of the other vertices within the graph. Let's start with this one, paths from vertex 2 to vertex 2. We could go along the path CB, going from 2 to 1 and then back to 2, or we could go along the path A, followed by as many copies of C as we like, followed by an A, followed by a B, and either one of these will take us back to 2. And then we can do that as many times as we like, going along either one of these paths or one of these paths. We could go along those paths 0 times, we could go along those paths 1 time, we could go along those paths 2 times, and so on and so forth. And that winds up describing all paths from vertex 2 to vertex 2. Looking at this term here, this bit here describes a path from vertex 2 to vertex 2, and then this bit here describes the various paths that we could take from vertex 2 to vertex 1. We could either go directly along the edge labeled C, or we could go via vertex 0 by taking an A, as many C's as we like, and then another A. And then for paths from vertex 2 to vertex 0, we could go from vertex 2 to vertex 2 as many times as we like, and then take this edge here, an A, and then take the C edge as many times as we like. And what's great is that these are all of the paths. It's clear that these are paths from vertex 2 to the various vertices, but it's not immediately obvious that we're not missing something. But because of the way that we've calculated this, because we've calculated these as entries of P star, the unique inverse of 1 minus P, we know for certain that these are all of the paths. So this is great if you want to turn a transition diagram for an NFA into a regular expression. All you need to do is calculate the inverse of a particular matrix over a particular algebra, and the regular expressions just fall out. I will admit, as you go further into the row reduction process, we're going to want to use this row here in order to do some canceling from these rows up here. And what that means is that we're going to want to take multiples of this row here and add them onto this row and this row. So the resulting first and second rows of this matrix here are going to be even more complicated than this row here. And they're going to involve the elements of this row. In a way that's a little bit more complicated than necessary, you're going to wind up getting regular expressions that are more complicated than they have to be. And you can simplify them down using some various rules for simplifying regular expressions. Or you could just rename the vertices and do this process again to get a somewhat nice formula for the row corresponding to your new vertex 2. So thanks for watching. I hope you now have a new perspective on the regular languages. Please leave any questions or comments that you have down below, and I hope to see you in a future video.